Welcome to the last part of the GOAP series. Today we will talk about optimizations and some extensions. Just a little heads up, some things I will talk about here are a bit theoretical, but don't let it stop you from applying it to your projects. Our depth-first search approach is O of D in memory and takes O of average numbers of actions times amount of goals to the power of D, or O of N times M to the power of D, with D being our planning depth, meaning our algorithm has exponential runtime. Obviously, we are asking ourselves the question right now, how can we reduce runtime? Unfortunately, I don't know of any way to reduce the runtime in the worst case, and I don't think anybody else knows either, but we could try to improve the average case. After I took my first AI lecture, I thought about making a faster planning algorithm by implementing A*, to search through the plans faster, and I suppose a lot of you thought of the same thing, and fear even did it. This is certainly possible, but I didn't do it, and I can't recommend you that you do it. First of all, you would have to define a clear condition when your desired state is reached, or define a good enough insistence value, which would serve as our goal. Then you would need to come up with a heuristic, which also needs to fulfill the condition of never overestimating the cost. Then the last step would be not to use a plain A* algorithm, but rather a iteratively deepening A* algorithm, because the problem we are searching for here isn't really like pathfinding. Let me explain. When we are trying to find a path with A*, we implicitly assume that there will be a path found, or eventually every node will have been looked at. In other words, we need to only have a limited number of possibilities, and in GOAP this is probably never the case. And there are even more requirements. But to sum it up, it's complicated and overkill, while probably only yielding a small speed up. So what else can we do about runtime? This is what I would do. I would split up the planning into multiple chunks, meaning I would remove the while loop part and create a method in the planner that lets the character plan for an arbitrary amount of iterations and save the partial results as attributes in the planner. Then I would create a boolean attribute that will be set to true when the planning is finished. What that allows me to do is spreading out the planning over multiple frames to not get lags. This is absolutely vital if you have multiple characters, and an iteratively deepening A* algorithm will almost certainly not give you the speed up you need to not get frame drops. Also, you have to remember that we are not trying to solve problems of existential philosophy here, we are trying to make a video game. So be pragmatic about this and use the easier solution. Google's AlphaGO Zero is a machine learning based AI, and also the first AI that was ever able to beat a professional human Go player, defeat a Go world champion, and is currently considered the strongest Go player in the world. This is especially impressive when you consider that there are more than 10 to the power of 170 possible board states in Go. Obviously we couldn't search through all of those states with our DFS approach. But AlphaGo still relies on planning. The planning AlphaGo Zero uses isn't exactly like GOAP we just implemented here, but I still think you can get some inspiration if you ever need to come up with a more complicated planning algorithm. Let's start with the action selection. Basically, instead of simulating every action, it generates a list of the strongest actions based on its experience and will only plan on those actions. Meaning, smaller trees will be generated, which is vital for the skill of AlphaGo, since it allows the network to explore the best actions more deeply, instead of wasting all its resources on one broad top level. Then, another thing which differs from the implementation here, is it also simulates the enemy's moves. So after each of the AI's moves, it simulates one of the enemy's moves, which it also generates based on its experience and current input data. For your personal game, chances are high that you cannot do this in your game unless you develop a turn-based game, but if you think this is possible for your game, then you should absolutely go for it. It will certainly improve your AI's quality and strength by a lot. If you want to see how powerful something like this can be, look up Minimax algorithm. Okay, back to AlphaGo Zero. Once it has simulated a move, it rates the state the board is in, similar to our discontentment function, but it only outputs a number between 0 and 1 on how certain it is that it will win this game given that board. I think the takeaway here is that you can create learned discontentment functions instead of handcrafting them. How exactly would you do that? Well, you must make your discontentment function a linear weighted function, and then you can learn the weights and have the AI figure out the weights on its own. That's also the reason why I said you ideally want a linear weighted function in the first video. Although I haven't done this yet, I definitely think this can work if you want to make an extra strong enemy for your game, maybe as a special event. Or maybe create an NPC copy of a very strong player of your game. Or if we move away from video games for a moment, even create a good discontentment function for some real world application. However, don't get too hung up on this. Most of the time a normal discontentment function will be just fine. But if you have a good reason, other than wanting to learn it preferably, then it can be worth a try. There's a lot more I could talk about in the field of planning here, but I feel like this was the most important stuff concerning GOAP, and I hope I was able to give you a basic understanding you can build upon, and most importantly, I hope I was able to give you an algorithm you can use for your application right now. That being said, leave a like on this video, and if you haven't done so already, subscribe to my YouTube channel for more computer science stuff. The next video will hopefully be out soon. Until then,